I am going to show you a trick to solving this MIT Integration B question. This appeared in the 2022 semi-final. So we can start off by distributing in x in the numerator, which is x e to the negative x plus x all over e to the x plus minus 1, and this one dx. So what I'm going to do next is to multiply top and bottom by e to the negative x, right? So the top I'm going to multiply by e to the negative x, and I'll have x e to the negative x plus x, and then dx. This one is divided by the bottom by e to the x as well, right, to maintain equality, and this is multiplied by e to the x minus 1. Alright, so we can now multiply in with the e to the negative x. So you have the integral from 0 to infinity of, this is now x, the numerator is now x e to the negative 2x, like this, plus x e to the negative x divided by this one times this is going to be 1, right, using the laws of indices. This is 1 minus e to the negative x dx. So this is what our integral has been reduced into. So this is the integral from 0 to infinity of x e to the negative 2x plus x e to the negative x, and this one I'm going to write it like this: 1 all over 1 minus e to the negative x dx. This is the same as our integral here, right? So this one, from the geometric series, we know that 1 all over 1 minus x can be written as the summation n running from 0 to infinity of x raised to the power n, right? This is from the geometric series. So if we have 1 all over 1 minus e to the negative x, this is the same as the summation n running from 0 to infinity of e to the negative x raised to the power n. And this is the same as the summation n running from 0 to infinity of e raised to the power negative nx. This is the same as 1 all over 1 minus e to the negative x. So in place of this one, I'm going to replace that with the summation n from 0 to infinity of e to the negative nx, right? So let's replace that in our integral. I is going to be the integral from 0 to infinity of x e to the negative 2x plus x e to the negative x. Then in place of this, I'm going to write the summation n running from 0 to infinity of e to the negative nx, and then dx, right? So I is going to be equal to the integral from 0 to infinity of, I'm now going to distribute in with this, that is now going to be the summation n running from 0 to infinity of x e to the negative 2x plus x e to the negative x, like this, which is multiplied by e to the negative nx, all this one dx, right? So I is going to be equal to the integral from 0 to infinity, the summation from n from 0 to infinity of, this is now x e to the negative 2x multiplied by e to the negative nx plus x e to the negative x multiplied by e to the negative nx, all this one dx. Now let's apply some laws of indices here. The integral from 0 to infinity, summation from n to infinity of, this is x, applying the laws of indices here, that is going to be e to the power, you factorize negative 1 common, this is now left with n plus 2 times x outside, and plus this one too is x, using the laws of indices here as well, that is going to be a negative 1 common, n plus 1, and x. This is what we have, and then dx. Alright, so I is going to, I'm now going to split this one into two different integrals and summations. So the integral from 0 to infinity, the summation from n from 0 to infinity of x e to the negative n plus 2 times x dx, plus the next one, the integral from 0 to infinity, the summation from n from 0 to infinity of x e to the negative n plus 1 times x dx. Now let's do some substitutions here, right? Here, the first one, I am going to let u to be equal to n plus 2 times x, right? And the second one, I'm going to let v to be equal to n plus 1 times x, right? So let's go back to the first one. Here, when we do that, what will be the change in limit? So here it implies that x is going to be equal to u all over n plus 2, right? So when we do that, the x is going to be equal to 1 all over n plus 2 du. Alright, so in place of the x, I'm going to replace that with 1 all over n plus 2 du. What about the change in limits? When x is equals to 0, the lower limit, you can replace it here. That is, u is going to be equal to 0. And when x is equals to infinity, the upper limit, u is going to be, this is positive, so that is going to be infinity as well. Right, when we come to the second one, when we have this, that implies that x is going to be equal to v all over n plus 1. So here the x is going to be equal to 1 all over n plus 1 dv. And now the change in limits. When x is equal to 0, v is going to be equal to 0 from here. And when x is equal to infinity, the upper limit v is going to be infinity as well, because this is a positive value. Now we can take the integral into the u and the v world. I is going to be equal to the first one. The limits of integration will not change. Still from 0 to infinity. That's from these ones. And then the summation n running from 0 to infinity of x. X is now u all over n plus 2. U all over n plus 2. And then e to the, this is negative u. So this is negative u. And then the x is the same as 1 all over n plus 2 du. That is our dx here, right? Cool. Now the next one is going to be plus the integral from 0 to infinity, the summation from n running from 0 to infinity of x here is v all over n plus 1. That is v all over n plus 1. And then e to the, this one is v, e to the negative v. And the x is what? The x here is 1 all over n plus 1 dv. So this is our integral in the u and the v world simultaneously. So I is going to be equal to what really? So here I can switch the summation and the integral sign. So that is going to be the summation n running from 0 to infinity. And then the integral from 0 to infinity of, this is u e to the negative u du all over n plus 2 times n plus 2 is n plus 2 all squared, plus switching the summation and the integral sign, that is going to be the summation n running from 0 to infinity, the integral from 0 to infinity of v e to the negative v dv all over n plus 1 all squared, right? So the variable here that we are integrating is u, right? So n plus 2 is a constant here and n plus 1 is a constant here, so we can just pull them out. I is going to be equal to the summation n running from 0 to infinity of 1 all over n plus 2 all squared. Then the integral from 0 to infinity of this one can be written as u to the power 2 minus 1, right? And e to the negative u, because u to the power 1 here can be written as 2 minus 1, right? And then du plus do the same thing here. The summation from n from 0 to infinity of 1 all over n plus 1 squared. And then the integral from 0 to infinity of v raised to the power 2 minus 1, because 1 here can be written as 2 minus 1, and then e to the negative v. Cool. Now we are going to compare this one to the gamma function. So if you have the gamma function, so the gamma of x, the gamma of a variable m, which is the same as m minus 1 factorial. This one can be expressed as the integral from 0 to infinity of x raised to the power m minus 1 e raised to the power negative x dx. This is the gamma of m, right? So if you know this to be the gamma of m, this one is going to be the gamma of 2, and this one is going to be the gamma of 2 as well, right? So we can just replace that in our integral. I here is going to be equal to the summation n from 0 to infinity of 1 all over n plus 2 all squared. And then this one is gamma 2. Then plus the summation n running from 0 to infinity of 1 all over n plus 1 all squared. And this one is gamma 2 as well. So gamma 2 is the same as 2 minus 1 factorial. And 2 minus 1 factorial is 1 factorial. And 1 factorial is 1. So the integral just reduces to the summation n running from 0 to infinity of 1 all over n plus 2 all squared plus the summation n running from 0 to infinity of 1 all over n plus 1 all squared. This is what our integral has been reduced into, right? So I'm going to write this one as, so the first one I'm going to use yellow. So the summation n running from 0 to infinity of 1 all over n plus 2 all squared. And then plus the next one, I'm going to use the blue pen. That is going to be the summation n from 0 to infinity of 1 all over n plus 1 all squared. Cool stuff. Now, what is this one summing to, right? We must find a value for that. So let's try to sum these ones. So the first one in yellow pen, when we plug in 0, what are we getting? That is going to be 1 all over. So this one is going to be equal to, for the first one in yellow pen, if you are summing from 0, the first one is going to be 1 all over 2 squared. The next one is going to be 1 all over 3 squared. The next one is going to be 1 all over 4 squared, and so on and so forth up to infinity, right? So let's put this one here. And now the next one in blue pen, that is going to be plus, right? So this one, when we are summing this one from 0 to infinity, that is going to be 1 all over 1 squared plus 1 all over 2 squared plus 1 all over 3 squared plus 1 all over 4 squared. And this one continues until infinity, right? So this is what we have for the first and the second one. But when we look closely, we see that this one is the Basel problem, right? The Basel problem is this one, which was solved by Euler. So that sums to pi squared over 6, right? So 1 over 1 squared plus 1 over 2 squared until infinity. This one sums to pi squared over 6. But this one is slightly different from the Basel problem. What we are only missing is 1. We don't have 1 here, right? If we have 1 there, then that one will sum to the Basel problem as well. So what I'm going to do here is to add 1 to the right hand side. For me to nullify the effect of the one on the left hand side, I have to add 1 to the right hand side as well. So I'll just add 1 here to the right hand side to nullify the effect of this one. Right, so when I do that now, this one becomes a Basel problem as well, because this is 1 over 1 squared, and this one sums to pi squared over 6 as well. So when we do that, then our integral now simplifies to I plus 1 on the left hand side, and this is equals to pi squared over 6 plus pi squared over 6, right? So this one sums to pi squared over 6. Now this is equals to 2 pi squared over 6, and that is equals to pi squared over 3. So we want I, not I plus 1. So I is going to be equal to pi squared over 3 minus 1. And this one is the answer to our beautiful integral. Yeah, so this is how I solve the integral. So when we go to the top, so we see that this beautiful MIT integration B question, which appeared in the 2022 semi-final, this one evaluates to pi squared over 3 minus 1. And this is the trick that I wanted to show you. So that is how to solve it. If you know an easier way to solving this, please leave a comment in the comment section and let me know what you think. If you enjoyed the video, please give me a thumbs up and subscribe to Calculus Diaries for more content, and I will see you in the next one. Bye bye.